Year 12, I've made a series of videos while I'm on Year 9 camp, Year 10 camp. So the first one is on exercise 2E and it's about network problems. Alright, so let's start. Okay, quite a long time ago, even before I was born, so in ancient times, in a town in Prussia, which is in between sort of Germany and Russia, there was this town called Königsberg. And Königsberg had 7 bridges, and here's like a really dodgy old picture of it. Okay, and here's the bridges over all the water. And people in Königsberg, mustn't have had much to do on a Sunday afternoon, would try and cross every bridge without going back over another bridge. Okay, and it became like the Königsberg problem. So that's an old picture of Königsberg. This is what it looks like today. And there's one of the bridges that probably still remain. So there's the river. Okay. So we're going to be looking at network problems. So straight out of your guided notes. If you have a knowledge of Euler trails and circuits, it's really helpful when you're solving network problems. What you're going to need to remember is that for a network to have an Euler trail, which is going over every edge once and once only, you must have 2 odd vertices, okay, and the rest must be even. To have an Euler circuit, okay, so starting and ending at the same place, going over every edge once, you must only have even vertices. Okay, so you need to remember Euler when we're solving problems with networks. All right, back to that Königsberg bridge problem. Here's like a plan view. Here's the 7 bridges. Okay, you'll notice there's a lower bank, an upper bank, and an island in that river, and a second island in the river, and there's 7 bridges. To solve it, we're going to turn it into a network diagram. Okay, so first thing I'm going to do is give myself the lower bank. So this whole area here I'm going to represent as a vertex. I'm going to do the same with the upper bank. Okay, so that area there is now my upper bank, and then we've got the 2 islands. Okay, so I've got my vertices, so my vertices are the land. My edges are going to be the bridges over the water. So if we have a look at this picture, there's a bridge going from the lower bank to the island, and a second bridge going from the lower bank to island number 1. So I'm going to put them on my diagram. There's the first one, there's the second one. Okay, there are 2 bridges, so there's 2 edges. Then from the lower bank, there's a bridge going to the second island. Okay, so I've drawn that in. Now I'm going to have a look from the upper bank. From the upper bank you can see there are bridges going across to both of those islands. So there's to the first island, second one to the first island. Alright, so I'll draw them in. There they are. And then there's this bridge here to the second island, drawn in. And then if you're on the first island, you can go straight to the second island over that bridge. So I've now created a network diagram. So the Königsberg bridge problem is, can all 7 bridges be crossed only once, starting and finishing at the same place? Now we could draw all over this, trial and error, or we can go, wait on, Euler's little trick. This vertex has a degree of 3. This vertex is 3, this vertex is 3, and this one here is 1, 2, 3, 4, 5. So I've got 4 vertices and they're all odd. So you cannot cross every bridge once and only once and get back to where you started. So my explanation would be something like, I should have written there are 4 odd vertices. I didn't count that very well when I typed this. So there are 4 odd vertices. This means that you cannot travel all 7 bridges and return to your starting position. Okay, alright. Okay, so this example out of your textbook says the network diagram opposite is used to model the tracks in a forest connecting a suspension bridge, a waterfall, a very old tree, a fern gully. Walkers can enter or leave the forest through either the first gate or the second gate. Oh, sorry, there's the fern gully. The numbers on the edges represent the times taken to walk directly between these places. A. Construct a table to represent the weighted graph. So here's a table, and I'm just going to fill it in. So waterfall to waterfall, it doesn't exist, so there's a line. Waterfall to gate 1, 8 minutes. Waterfall to the Fern Gully, you can't get there directly, so nothing. Same, waterfall doesn't go to gate 2. Waterfall to the very old tree is 10, and waterfall to B, the bridge, is 9. Okay, so I'm going to quickly go through from gate 1 to the waterfall, 8. Gate 1 to gate 1 doesn't exist. Gate 1 to the ferns, 8 minutes. Gate 1 to gate 2, you cannot get there. Gate 1 to the tree, you cannot get there. And gate 1 to B, the bridge, is 6. Okay, so I'm just putting the numbers into the right place in the table. Now I'm at the Fern Gully. F to the waterfall doesn't exist. F to gate 1, 8 minutes. F to F doesn't exist. Oh, F to gate 2 is 10. F to the very old tree doesn't exist, and F to the bridge is 12 minutes. Okay, and I can keep going. Gate 2 to the waterfall doesn't exist. Gate 2 to gate 1, can't get there directly. Gate 2 to the Fern Gully is 10. Gate 2 to gate 2 doesn't exist. Gate 2 to the tree is 6, and gate 2 to the bridge is 8. Okay, and filling in the rest. So from each vertex, I worked out, the times between those two vertices. Part B says, what's the time from the bridge to Fern Gully? Well, I can use my table. Bridge to Fern Gully, 12 minutes. Or I can check, bridge to Fern Gully, 12 minutes off the picture. C says, how long does it take to walk from the old tree to Fern Gully via the waterfall and the bridge? So 10 plus 9 plus 12 is 31 minutes. All right, you've got questions to do out the textbook. Enjoy.